Hi, I'm Krishna. This is our new lab, changes in energy. So there are many ways of analyzing the motions, and in this lab we are going to analyze the motions by using changes of energy concepts. So basically we are going to discuss about the two kinds of energy in this lab. One is kinetic energy and another is potential energy. So in the kinetic energy, when the center of mass of an object moves, then we say that the translation kinetic energy changes. So when the object moves about the center of mass, then we say that the rotational kinetic energy changes. But in this lab, we are not going to focus about rotational kinetic energy. Our only goal is to focus on translation kinetic energy. And the formula for kinetic energy is kinetic energy equals 1/2 mass times velocity square, and the unit is joule in SI. And another energy is the potential energy. So when the object moves farther from the center of the earth, then we say that the gravitational potential energy of the object is increases. So the potential energy is related to the position of an object. Position. Energy, and the formula for the potential energy is mass times acceleration due to gravity times height from the reference level. So the energy, the unit of energy is joule. So the unit of potential energy is also joule in SI system. So in this lab we are going to relate the gravitational potential energy with the positions, and we are going to say that whether the gravitational potential energy increases, decreases, or remains the same. And the second thing is that we are going to relate the height positions with respect to the velocity. And another thing of the objective of this lab is to define the conservation of energy, to prove the conservation of energy, how the energy is conserved by analyzing the motion. So let's go to this picture. This is the roller coaster, and we are considering the reference level. This is the reference level, and this is the height. This is the point. Let's say this is point O. So when object moves from this point O, before object moving, the velocity of the object at the point O is 0, right? So when object moves, then it gains slowly the velocity. We can see that from the blinkers, the length of the blinkers is smaller here, and then little bit larger, and then it increases up to this point, and it again decreases from this point. So at this point, the potential energy is mgs, and the object suddenly lost the potential energy, and it's converted into the kinetic energy. So we can say that loss in potential energy is equal to gain in kinetic energy. So let's assume this is the point A, and this is the height del S. So this is our space level, and okay, when the object is at the point A, then it loses the potential energy, right? And the loss in potential energy is equal to mg del S. And object gains its kinetic energy. At this point, the velocity is 0, so the velocity is 0, and then object suddenly gains the kinetic energy at this point because the velocity is increases. So we can say mg del S equals half mv square. So another important thing is that we are neglecting the friction forces and some other dissipating forces like heat, so that the loss in kinetic energy, loss in potential energy is equal to gain in kinetic energy in this case. So mass is cancelled out, and del S equals 1 over 2g v square. So 1 over 2 is constant and g is constant in our case. So del S change in height is directly proportional to velocity square. Or we can write velocity is directly proportional to square root of change in height. So if you know the change in height, we can say the velocity of an object. So let's assume there are two kinds of path. This path and this path. They are on the same height. Let's say this is height S. Suppose at first the object moves in this path, and the second case object moves in this path. So when object reaches at the point, this is the reference level. When the object moves, when object reaches at the point X, then it only goes from the height S, right? So we can say that velocity of the object at the point X is same for the both case. It doesn't care about the nature of the path. This is the steeper path, this is the shallower path, but when object launches from this point, when object reaches at this point, then the velocity, final velocity is same for both the cases. So the nature of path doesn't care about. So if you know the change in height, we can say the final velocity is directly proportional to change in height. Okay. So this is the important relation. So you can use this relation while solving your lab questions. And so I can erase this part. So while choosing the reference level, we can choose the reference level as our will. We can choose the reference level at this point as well. We can choose the reference level at this point as well. We can choose the reference level at this point as well. So it's up to us. So I have to choose the reference level top. So I am going to verify the conservation of energy. Conservation of energy. Let's assume our reference level is at this point. So this is our reference level for this case. So at reference level, the potential energy equals 0. And then before releasing, the object is at rest, so the kinetic energy is also 0. So we can say that at this point, the object has the kinetic energy and the potential energy is 0. So the sum of kinetic energy and the potential energy at the point A is 0. The total energy is 0 at point A. So we can say that the total energy is conserved. It means that the total energy at this point B, and this point C, the total energy at this point B should be 0 and C should be 0. Right? Okay. Let's draw this. Let's draw the kinetic energy and potential energy, the Bayer diagram. This is the reference point. 3, 4. This is point A. Point B, and this is like potential energy at point A and potential energy, kinetic energy at point A, and this is potential energy and kinetic energy. Alright, okay. So this is our reference level. So at the point A, the potential energy and the kinetic energy both are 0 because potential energy is 0 obviously, because this is our reference level, and before releasing the object is at rest, so the kinetic energy is also 0. So we can just draw the potential energy something like this, because this is the 0 level, right? And the kinetic energy is something like this. Okay, let's go to the point B. Point B, the potential energy is 1, 2, 3 step downward, right? So point B, the potential energy is 3 step downward. So we can draw the potential energy something like this: 1, 2, 3. But the total energy at all the points A, B, C should be 0. So if the potential energy 3 step downward, so the kinetic energy should be 3 step upward in order to conserve the energy, right? So we can draw the kinetic energy something like this at the point B, because the potential energy 3 step downward, so the kinetic energy will be 3 step upward. Similarly, we can draw at point C, the potential energy is 1, 2, 3, 4, 5, 6 step downward. So potential energy is 1, 2, 3, 4. This is 5 and this is 6. So the potential energy is 6 step downward. So you can write the potential energy something like this. You can show in the bar diagram. And the kinetic energy should be 6 step upward, because in order to conserve the energy, right? So we have to go 6 step upward. 1, 2, 3. This is, let's say, 4, and this is 1, 2, 3, 4, 5, 6. So we have to go up to 6 steps. So this shows that the potential energy sum of the potential and the kinetic energy at point C, B, and the A are equal, and it is equal to 0. So we can. This is due to the conservation of energy. Energy is always conserved if you neglect the frictional force and other some dissipating forces. Okay, this is the point. You can start.